So one other thing that's cool is we talked about von Neumann's stored program concept. What was von Neumann's stored program concept? I've seen the answers there. What's von Neumann's stored program concept?
It's to do with software and bits.
True. Take it to the next level. Von Neumann stored program concept said
you can change the program without changing the hardware.
Maybe. We can make it more specific. Stored program says we'll represent instructions as bits. Remember we said we represent data as bits. I think everybody knows that. Everything's bits, right? Data's bits. But what about instructions? Von Neumann said store instructions as bits. Remember we had I gave you the mechanical analogy, which we had the Jacquard's loom, and we saw the bits, right? We saw the punch card. That was instructions. So now we're going to see for MIPS, how do we store instructions as bits? We're going to actually see von Neumann's program concept, and we're going to learn some new instructions. So this helps us translate to machine code. We're going to actually see the bits. We're going to have some new instructions. We actually covered SOL already, but we're going to cover some other ones. And how to write more sophisticated programs, which is the downside because then you have a new project. We'll look at moving different size data elements too. So we're not going to learn just bit encodings, but we're going to learn more about how we store data as bits. We talked about a word, load word, store word. We're going to talk about loading and storing bytes. What's the difference? When we load and store bytes, usually we access characters. So where are we? If we look at the chip, we're talking here about data and instructions. Data, when we talked about storing bytes, going to be somewhere in the cache. We're explaining what these means. There's a data cache and instruction cache. Okay, we'll talk about that. And logical unit is how we're processing these. So let's see instruction encoding. Von Neumann's stored program concept. So MIPS instructions are always stored as binary strings. Actually, every processor instructions stored as binary strings. We have 32 bits, or one word, per instruction. Because MIPS, 32 bits is the data size, it's a word size, and it's also the instruction size. We have opcode field and operand fields, just like when we wrote assembly. There's some values that are assigned, which are constants, that tell us, remember T0 register, S0, and so forth. They have register numbers. We had a table earlier. We're going to use these numbers as part of the instruction encoding. So let's see an example. Here is the instruction encoding. This is on your testing reference sheet. Do I have to memorize this? No. It's on a testing reference sheet. We have 3 different instruction formats. Can anybody give me an example of an R format instruction? That would be like add. Why? Because we're going to find out we have RS is a source register, RT and RD. T comes after S, right? S before T. These are input operands. This is destination. We have some other fields here. We're going to explain these. But that's for an instruction like add. And we're going to see examples. You also have immediate format. Anybody give me an example of an immediate format instruction?
Load immediate.
Load immediate.
Add immediate.
Add immediate. Yes. Subtract immediate. We have a constant. Where does the constant go? That's this immediate value. And the immediate value is the constant. We'll talk about these. There's 32 bits total, and each one of these has a certain number of bits. Before I go to the next slide, if this is a register, why are all the registers, the register field, this is the width of this field, why is the width of that field 5 bits? To specify a register, why? In MIPS. Bless you. It could be 5, it could be 100, it could be, how'd they come up with 5? Why 5? How many registers in MIPS? 32. How many bits do you need to specify a value? 32 distinct values. 5. 2 to the 5 is 32. If you have 4 bits, how many distinct values? 16. So we're going to see, actually, the number that's sitting here, it's a number, it's a binary number, but we don't let that bother us. It's the same as decimal digits, except there's no number greater than 1. That number that's sitting there is telling us the register number. The number that's sitting there is telling us the register number. Which register number? Remember the source and destination where we're moving data in and out? And you say, is that it? That's it. Okay, let's take a look. Here's an example. Here's a register format instruction. It's not immediate. Okay? And it's not, we had 3 choices, right? We have register, immediate, and jump. It's not a jump. And it's not immediate. And this is the mapping, and we had a question.
Why are some of the 6 then, if we can only accept 32?
Good question. Let's take this one. Exactly. Not a register. But let's go to the next level. How many different opcodes can a MIPS processor have? You got it. 64, because 2 to the 6 is 64. Why do we learn powers of 2? Everything's encoded as bits. Somebody shows you how many bits, you know exactly what it can do. If they give you 5 bits, that's 32 choices. If they give you 6 bits, 64 choices. Can it ever be different? Well, we can say the bits mean different things, but it can't be more than 64 choices to give you 6 bits. That's the max. Maybe they don't use all of them. Turns out MIPS doesn't use all of them, but we'll explain, yeah.
Is the
Great.
immediate 21 bits?
Which one?
Immediate?
Ah, awesome. So this is 32 total, and this was how many? 5. So 6 plus 10 is 16. You start with 32. So you're in the test, and I didn't tell you immediate. How many is immediate? 16. You're ahead of me. That's the next slide. So let's take an example. You're given an arithmetic instruction with operands. There it is. What's that? Instruction bit encoding. I color-coded this for you so you can see it, okay? How do you solve this problem? You're going to specify the bits in the register format. First, you have to identify that I need to know its register format. How do I know its register format? Well, it's not an immediate mode, and it's not a jump. The cool thing is MIPS only has 3 instruction formats. You go to Intel, they have 57 different instruction formats. 400 instructions is too complicated. So what do we do? Let's take the easy ones first. T0 is encoded as a number. Is T0 a destination or a source? Destination. Destination is the RD field. And you're going to say, well, why didn't they put it over here? When they wired up the circuit, that's just how the wire's laid out. So T0 is stored as a number. How many bit number? 5 bits. What number is that? 8. Where do they get the number 8? It's the register number 8. Remember the register file? What is this? A register file. What about T0? What register number is T0? 8. They go in order. Does everybody see why? T0 is encoded as the number 8. Is this a decimal number or what? If I don't tell you any base, it's always decimal. How do I represent 8 as 5 bits? What does it look like? I have 5 slots to fill with a 1 or a 0. Yeah. Nope. Yeah. 1, 8. I said no 1s, no 2s, no 4s, an 8, and no 16s. So if I look inside that field, but you can put a logic analyzer on it, and then you'll see those bits. How do you see the bits electrically? What does it mean? There's a voltage, right? If it's a 0, it's 0 volts. You put a voltmeter there, it's going to read 0, and if it's a 1, it's 1.2 volts or 2.8 volts or whatever your processor's high voltage is. That's it. Sub, actually we're going to see, is represented as the combination of 2 different fields, and they don't do that to be complicated. It's actually to make it fast. Anytime you have a 0 here, you have to look in this field to see what the operation is, but it means that it's an arithmetic instruction. When it's a 0, we'll get back to that. What about S1? S1 is the RS, and this is the RT. This is a source, and the next source, if this is S, then the one more is T. That's how I remember it. It works most of the time. There's a few exceptions. So we start with the instruction. We want to get to the assembly language instruction. We want to get to the machine code. This is basically mapping from the human view to what the machine actually represents this information as. It represents it as bits. Whose idea was that? John von Neumann, stored program concept. Everything's bits, whether it's data or an instruction, it's bits. How did he determine this? We kind of stepped through it, so the next slide can go fast. Here's our format table, and we see some examples, some instructions you know. Add, sub. And you can see what these different values are. These seem like random numbers, but actually 32 is a power of 2, so that one bit is set to 1 and everything else set to 0. It's kind of like, to human it looks 32, looks a strange number, but to the machine it's just looking for that one voltage. All right. Again, we have our register encodings. You can go back to the register table and you can see where these numbers came from. We give you this on the testing reference sheet. So, here's an example. For our format, it goes op, rs, rt, rd, shift amount, remember shift, and a func. So here we're given another instruction, right? Determine the bit stream. So how do you do this? You convert each field one at a time in the format. This format is given on the testing reference sheet. You have to know it's our format. Is that hard? Well, it's multiple choice, there's 3. It's not immediate mode, it's not a jump, it's R. Good. Look in the R format, you got to figure out the opcode, such and such and such. It turns out, you look in the table, and you say, what table? Let's make it real. This was the what? Add instruction? The op field is 0 and the func is 20 hex. You look it up. What's 20 hex written as decimal? 20 hex is how many 16s and how many 1s? 2 16s and no 1s, right? 0x20 is what? Remember binary, I said this is 0 what? No 1s, no 2s, no 4. So this is hex, right? Because this means hex. What is this number? This is 0 1s and 2 16s. This is 16 to the 0, 16 to the 1. So this is 2 times 16 to the 1 is 2 times 16 is 32. You're good to go. You're going to say, you know what, how do I remember that? Well, decimal, it's the same thing, right? You know, 1, 3, 7, 4 is 4 times 10 to the 0 plus 7 times 10 to the 1 plus 3 times 10 to the 2 is 100. 1 times 10, it's the same. So what do? So you write each field. What's S? 17, that's in the table. How do you write 17 as a binary number? What's the nearest power, largest power of 16? And what, plus 1? If you have 17, how do you get to 18? You go one more. So how do you go from this number to that number? Go from 001 to 10. You guys got it, right? Yeah, you can convert this. They divide in the fraction and the 0.5, and yeah. Well, for small numbers, 5 bits, you can use their powers of 2. Just always remember, it's no 1s, 1, 2, no 4s, 1, 8. You got it. Okay, so we got all the fields. What's the actual number that's stored in memory? You're going to say that's too hard to write, and you're right. So as humans, we like to use hex. Hex is a human readable form of binary. I mentioned this before, we mentioned it again. You end up with a sequence of bits, right? 6 zeros, this number, this number. To write hex is a lot easier than saying all those 1s and 0s. This is 4 digits of 0, which is hex 0, and then what? What number is that? 2? 3? How many hex digits if you didn't make a mistake? Because it's easy to make a mistake. If you didn't make a mistake, how many hex digits do you end up with for a MIPS 32-bit word? How many hex digits? 8. 8 because each one is 4 bits. You have 32 bits. Each hex digit represents 4 bits. You better have 8 down here. If you don't, just go back and it's telling you, you skip something, which is. Of course, we want to know how it works so we can design it, but we're getting there. Let's try another instruction format as immediate mode. This is the I format. How many registers do you have? How many operands do you have in an immediate mode? You have one destination, one source, and a constant. One destination, or source, destination. One destination, one source, and one constant. This is a little bit tricky. Yeah, source. RS is usually the source. T is after S. If you don't have another register, it's got to be the destination because everything is a constant. What's the range of this constant? We have 16 bits. We were set on the right track. We start with 32. This was 6, this is 5, this is 5. It's in the testing reference sheet. So that's 16 from 32 leaves us 16 for this field. It's guided at 32. I give you 16 bits. How much of a number, how large or small number can you represent? Now we're starting to get to positive and negative values. So if I use a representation that's signed, right? We have unsigned and signed. If it's a signed value, I need 1 bit to tell me if it's negative or not. I start with 16, so how many are left? What's the range of the number? 2 to the 15, plus or minus if it's, right, positive or negative. You guys got it. So here's some design compromises. I have 32 bits to work with because of the 32-bit processor. I have to make some decision. If I have more registers, what happens to the size of the constant? Less. If I have a smaller constant, I can have more registers. What's better? Depends how many times we have to access data and what percentage is immediate mode and what percentage is register mode. Will somebody want to analyze that? Yeah, if you want to make it faster, you want to make better use of the resources. So here's a step-by-step process to obtain this. This is a good problem, but we've already looked at for a register format. Let's look for immediate. Here's an instruction. So how does these problems work? They give you this.
4 plus S1.
And they want you to come up with this. Express your answer in hexadecimal. So how do you do it? Well, you've got to figure out the value of each field. How do you do that? Use the testing reference sheet to look up the register number, write that in binary. Look up the opcode, write that in binary. Then what? You got a whole bunch of binary digits. You got to write it in hex. You guys know how to do that? Just group them by 4. Let's try another example. We had one more encoding is the load word. Actually, load is immediate mode encoding. Remember this offset of 24? That's going to be encoded here. Opcode for LW is 35. It's in the table. You notice when we have op, you don't have a func. Func and op work together. We'll see more examples. We can look up this value. So what's RS? Okay, kind of interesting, right? We have to get a base register S3. S3 is register number 19. It's in the table. How do you write 19 as bits? 16 plus what's that? 3? Seeming really straightforward now, right? I know when they teach you it, they make you do this divide thing, and then, yeah, but I look at this, I see 16 plus 3. That's what it means. Instructions and codings, module 6. This is a good one to start from what we covered last time. This is bringing together a few concepts, and we're going to put them together and build on it. Here we have an address that we're accessing via an arrayed value. This is an array that's in memory. It's an integer array. A sub 300, we're going to add some constant to it, or variable in this case, h, which is already in a register. It's mapped to a particular register. and the base is in T1 of array A, and the output goes to the array. So before I even get any further on this, we think, what are the transfers that have to occur using an abstraction model of processor and memory? Right? So where is this information? So first we have to do an addition, right? But before we do an addition, we have to get data inside the processor because that's where the adder circuit is. Where is this information?
Memory.
It's got to be in memory. Anytime there's an array, it has to be in memory. So we're going to need what instruction? For sure. Load word. Then we have to do an addition. What about H? Where is H? We can do the addition right away because H is in a register. All right? Okay. We've got the addition, then what do we need to do? Put the result into A sub 300. Where's A sub 300? Is in memory. That's a store instruction. Okay. So everybody, that was the previous modules, right? And the exam. Everybody can write these. What we're doing, so you're going to say, okay, that's fine. Well, what are we doing in this module? So what we're looking at now is the actual bit representation of each one of these instructions. Von Neumann's store program concept was not only represent data as bits, information as bits, but also instructions. The processor is going to read those bits and use those to activate the circuit, which we show soon. So here we have 3 different instructions corresponding to I1, I2, and I3, instruction 1, 2, 3. And there's different formats. So we had last time register format, I was immediate format, and jump format. So the first question is, what are these formats? It turns out the LW and SW, because they have this constant, they need a constant field that uses the I mode. So according to the instruction encoding table, you're going to say, what is that? Instruction encoding table is what we started the slides with. If it's I format instruction, you have op, rs, rt, and then the constant. Let's take a look. We have op, rs, rt, and the constant. So what is this constant? So the constant here is 1200. This is 1200 written in binary as 16 bits. Okay. So how many bits do we have? So here we have what? If you convert this, what is this? And let's do hex, right? So if this is hex is 0, what?
1632 and
This is, we're going to write these as hex digits. 0, 4, 11. See the 11? It's 10 is 10, 10, right? And it's 11, 0. So we take that hex and binary is the same thing, right? So what is that? Well, different ways to, you take hex, and I don't expect you to be able to do this right off, but actually it's not. We'll show you the easy way to do it. If I change this into a programmer. So we had 4B. Give me a hex, thank you. B0. Nope, clear. 4B0. And convert to decimal if I just do this, right? 1200. So indeed, this is 1200 written as bits. So where does that come from? Well, what's the largest power of 2 that goes into 1200? It's 1024, which is 2 to the 10th. Right? This is 2 to the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1 1024 plus what? 1200 minus 1024. Okay. So this is how we get the bits. We're going to put here first the constant. The constant's the easiest one to get. And what about the other things? Well, LW has a sequence of bits. How many bits? It has 6 bits. That's from the table. Let's just actually get the testing reference sheet rather than going to the slide. Let's get the testing reference sheet to show where these come from. And you want to practice using it for the study set and the exam. If I go here to here, testing in here. LW is 23 hex. So what is that in binary? Good question. Binary like what? How many bits? Op is how many bits? 6 bits. So how do you write 23 hex as 6 bits? So as 8 bits, that's 2. And what's 3? 1 more than 2? Good. But this is 6 bits. So what do we do? Go back. One zero zero zero. I don't remember why that's blue. 100011. Okay, looking good. What about register numbers? What's that in decimal? Come on, guys, wake up. What's this in decimal? 9. Good. What's this? 8. Good. Register what? T1, T0. So the question is, what's the source and what's RS and RT? It depends on the instruction. For LW, okay, what is our format? Sorry to go back to the sheet, but I'll go back to the sheet. It is RS and then RT. So we see here that this is a source, right? And then, okay, so RS, RT for LW. What about SW? SW, it's going to use the same position notation, right? So actually this is the RS, see? And RT. All right, well, store word, even though this is really a destination, it's coming in as the RS. That's just how we do it. I said there are some exceptions. This is one of the few exceptions. So normally when we look at this sheet, we've seen several already. Register format usually are not too tricky or too complicated, and there's only a couple exceptions. Load word is one of them, but you can see that if we have register format, RS, RT, RD, when we write it as assembly, RD is the first operand, closest to the opcode. We have immediate mode, it's RS and RT in that order. Normally S is the source and T is the next register, whatever it is, but in case of load word and store word, you have to keep them straight, and here's an example. What about the add instruction? Add is what format? I just said. R format. R format is opcode, S, RT, and RD. So the destination is T0. T0 is register 8. You're going to say, where did you get that? Go to the testing reference sheet. T0 is register 8. Okay. So we write 8 in binary as how many bits? In this case, 5 bits. Suppose your testing reference sheet broke, and this is not, those pixels are missing from the display, and it's bad luck, but that's the way it went. And you can't read this over here. How do you know how many bits these registers are? It's covered up. We need 30, we have to address any of 32 registers. There's 32 distinct choices. I need 5 bits. So it's always 5 bits for registers. If the machine had 64 registers, then you could have 6 bits in that field. Or if the machine had 128 registers, you'd have 7. 2 to the 7 is 128. So this should not be a mystery. This should not be a mysterious thing. They should all make sense. It should make sense multiple ways. Why? Because you understand the hardware that's beneath this. We're actually trying to access a register. A register has a number. We have tables for that, but we encode those as bits. You get to the end, if you don't have exactly 32 bits at the end for each one of these instructions, go back and check, maybe you dropped a bit. So each row corresponds to one of these instructions. The programmer typed this, or the compiler generated that from C code. What the machine actually executes is it fetches from memory an instruction containing this bit sequence. That bit sequence, we're going to see, activates the circuit to do the steps required for load word or add or store word. and we'll explain it. Sometimes they ask the same question, but they ask for decimal. Okay? So this is the same exact question, asking for decimal. This is actually from the book. And he shows here the decimal values. It's actually easier. Maybe you want to do decimal first and then get the binary. Should probably change the order of these slides. I'll let you ask any question on encoding instructions as bits. Takes practice, but first step is identifying the format R, I, or J, okay, which we'll see some example of J soon, okay. Register, immediate, or jump. Once you've identified the format, then you know the fields. It's a matter of filling in the fields with the correct value, and they're represented in binary or hex or decimal, whatever the question is asking for. Why do we ask you different formats? Because sometimes you hook up a logic analyzer, it's outputting hex. Other times you need binary because you're going to connect a wire and you have to know exactly which wire it is. Sometimes it's decimal because that's what the data sheet gave you. We just get used to using these because sometimes one is more convenient than another. We already did immediate encoding. Here's another one, just showing each one of these fields, and it doesn't hurt to keep practicing these, and we're going to get to some interesting things about this constant, and it could be a positive or negative. So constants are specified as part of the instruction. I mentioned this, that sometimes we don't have to go to a register or to memory. We can encode a constant as part of the instruction, so we see that happening here. Okay. Here's an example. Here's add immediate. It turns out add immediate is actually implemented by some constant. If you want to subtract, they can use add immediate of a negative value. So we're going to show you how to represent negative. You're going to say, well, why didn't they make a sub-immediate instruction? You can do sub-immediate as a pseudo instruction, but on the chip, they can just flip this to a negative number, and they don't need to have hardware for a sub-immediate instruction and an add immediate instruction. So what does this encoding look like? It's immediate mode, so it's op, rs, rt, and constant. As I mentioned, this is 32 bits. So this is 6, 5, 5 is 16. That means there's 16 left over. It's a 16-bit we'd mentioned last time. Constant stored inside the instruction. Here's the range, so it could be positive or negative. We need 1 bit for the sign. That leaves 15 bits for everything else, which is the value. So we've talked about these before in yellow, the general purpose registers. Now we're going to start to see some of these other registers as we go forward. But when we talk about general purpose registers, they're basically T and S. And these are the register numbers, but they're in the table. A lot of times we'll give you an instruction and ask you to write the bit representation or machine code. You need to know what register number that is. And these are the register numbers that's in the table. Let's look at some other instructions, and then we'll look at their bit representation, because we haven't talked about the field called shift amount. Is SAMT, shift amount. So certain instructions use a shift amount field, and those include the shift instructions here. So these are an instruction class called logical. So what are some of the instruction classes we covered so far? Yes, arithmetic. Give me another instruction class from previous modules. Branch is control flow. Excellent. And there's one more we covered so far. Data transfer, load word, store word. So here's another instruction class. A lot of times they're lumped together. Logical and arithmetic becomes arithmetic logical, but actually they're subclasses. So here's a logical means bitwise. So we're going to give examples of this. You can express the same in C. If you do a double ampersand, it's what they call logical and. If you use a single ampersand, it's bitwise and. We'll show you what that means. This is the MIPS versions of those. We already talked about SLL, shifting left, shifting bits, multiplies by power 2. These instruction class, which is a logical instruction class, those are good for inserting, extracting, modifying bits, bit Boolean operations. Let's show you how we can extract, modify bits. This is very important. If you're making a sensor, it has certain bits come in. Each one of these bit fields, just like the instructions we saw, have a different meaning. One is the sensor value, another is a control flag that says if the data is valid or not valid. You have to go and extract those, because your job is, you work for Harris, you're electrical engineer, you've got an antenna and it's sending this data in, and you have to pull out that field that's the data that you want. We can use these instructions. So here's an example. What saw is the MIPS instruction to return T0 only the lowest 4 bits. So you have a sensor connected up to the processor, and there's an I/O port. That's embedded systems. That's the next class, but we get you started. So what happens is, what's contained in T0 is by default 32 bits, but we only care about the lowest 4 bits. How do we extract those to do something with them? Like to test those lowest 4 bits. So what we can do is we can use AND function and use T1 as a mask. So the semantics of this instruction says, do what? Take T1, which is this string, which is a mask, 15, C15, written as binary, is 15 decimal. Anytime we don't have a number, it means decimal, right? A base, right? So 15 is decimal. This is 15 decimal written as binary in 32 bits. And then we AND that with T2. So T2 is just whatever's in that, I'm sorry, S2, T2. T2 is whatever's in that sensor's status register. It was sent to the processor. Well, it's a bunch of bits, and I can make it more complicated, but here's some bits. What's the output is the destination, T0. What we've done here is we've masked off all the bits except the lower 4 bits. And what this means is we do 1 and 1, because AND is bitwise. 1 and 1 is 1. What's 0 and 1? 0. 1 and 1 is 1, 1, 1. Now, since the mask had zeros for all this, these are automatically all 0. So it's just like masking tape, okay? You're going to paint your room or whatever, and you don't want it to get on the windowsill, and you put masking tape. What does it do? It masks away whatever you're painting, right? And it masks it off. So we mask off bits, and you'll see this bit mask. It's like masking tape. So the key thing, the takeaway here, is AND is 0 sensitive. Okay? Anytime we see a 0 and we're ANDing with 0, I already gave the example, right? You have a big circuit, and at the end you have an AND gate, and a 0 comes in. You don't have to even analyze the circuit, right? And I have a bunch of gates here, and a bunch of gates, and a bunch of gates, and stuff over here. F is 0. Why? Because AND is 0 sensitive. As soon as a 0 comes into an AND, whether it's 2 input AND, 3 input AND, 10 input AND, we don't usually build more than 4. But anytime an input of 0 comes into an AND, because AND is 0 sensitive, the output's 0. That's the end of the story. So what this means is if we set a mask with 0, we're only going to be left with the bits that the mask is 1. I'll let you ask any questions. And this is this example of a logical instruction class. And we have AND, OR, and so forth. We'll show some examples of OR next. So we want to return only the lowest 4 bits unchanged and all the other bits set to 1. Interesting. Okay. Why would you want to do that? Well, now we're sending data back out to the sensor, and it has a data sheet and says that the uppermost bits must be set to 1, or it has some other behavior you don't want. That's the way it wants the data. So how would we do that? You can use a logical OR instruction. This is bitwise. So T1 ORed with T2. T1, T2. What do I picture happening? We have T1 and T2 get ORed together. All right, is ORed, and the result is going to go into T0. This is bitwise OR, so we look inside T1 and T2. If these are the values, right, that we have, what do you think is going to happen? Since this is the OR mask, all the bits that are 1 are going to be propagated to the answer. See the answer here? So anything that's a 1 here comes in the output, as well as anything a 1 in the other input. We say that OR is 1 sensitive. Just keep it in mind. Yeah. Good. Good. Yeah.
Would that change the number to a negative number, like the last?
Well, actually, you're right. And since that's the next slide's coming up actually soon. Further than I thought. But we're going to talk about negative. The most significant bit is a negative. So we're going to get. So one way to make a number negative If it's 1's complement, which we don't use too much, is you can use a mask of just 1 here and all the other bits unchanged. Is a mask of an OR, right? We'll just OR and a 1 make it a negative number. We'll give an example. That's a good question. But we say, remember, AND is 0 sensitive, OR is 1 sensitive, and that was like what? A month of 3342? But that's all you need to know. So suppose you want to flip the bits inside a word. Sometimes we want to do that. And we can use a NOT instruction. A NOT is an intrinsic instruction in MIPS and practically every processor on the planet. One way to do this here is we can do this a few different ways. If we don't have a built-in NOT, we can use a NOR, which actually is intrinsic. Okay. And if you do the math on this, in Boolean math, you see that x NORed with 0 is not x. You'll see for all the cases of 1 and 0, every bit gets flipped. So if this started with a 0, and you NOR it with 0, it becomes a 1. Any 1 NORed with 0 becomes a 0. It has a NOT function. Okay. So why use this instead of NOT? You can type NOT into Mars. Mars will convert it to this. Because in MIPS, they already had NOR, and NOR can be done as a NOT. This way they saved writing the NOT instruction. Designing the circuit for NOT instruction because it can be realized as NOR.